What is up, YouTubers? I'm going to do a video here very briefly, I think, on scatter graphs, which is mostly for my AS maths class.
I'm afraid we need to use math.
So I'm just going to take a look at this one example, which I'll send you this handout on scatter graphs. Again, it's not that easy to see it, perhaps, when I record it on my phone, but I'll send you a copy of the handout. But it says the table below shows the engine size in litres of various cars and the distance travelled in kilometres on 1 litre of petrol. So, in other words, the engine size of a car is kind of a measure of how fancy it is. If you have a bigger engine size, then your car can go faster, let's say. But it may be more expensive to run it, and let's see if we can find evidence for that then using this data set. So there's the various different engine sizes of cars and also information about how far they travel on 1 litre of petrol. Now, plot this on a scatter graph. I'm going to plot this out. I've just drawn the axes on at the minute. Engine size across and distance travelled on 1 litre up and down. And then plot the points. So you go across for the engine size. The first point is 0.8 engine size, which would be there. And then it travels 13 kilometres on 1 litre of petrol. So I go up to 13 and plot the point, which would be there. So I'll do that with the rest of the points here. So I've got my points plotted. There they are. And in order to analyze out these results, we can see that it's not difficult to see that they're in a pattern and that they're approximately in a straight line, but we need to be able to be more precise about it. So let's see how we might do that, or how we should do it. Our engine sizes are X's, and the distance traveled is our Y's, and that's our data set here. And we want to see how those two quantities are related to each other. So we need, I'm going to sort of make it more concise and just write it like that, or just X's and Y's. We need columns in our table calculations for x squared, y squared, and xy. Now, that's not difficult to understand what that means. You just need to square the x. So I'll fill the rest of this in a minute. That's x squared. That's y squared. xy just means multiply. 0.8 times 13. I think I will use a calculator. So 10.4. So I'll fill in the rest of the columns and then we'll see what we can do with these numbers. Here we go. The columns have been filled out, and I will explain how we can deal with these numbers. First of all, just to keep it as easy as possible, first of all, one thing we need to do first anyway is take note of the mean of the x variables and the mean of the y values, because actually if we plot that as a coordinate point on the scatter graph, then that is usually good practice, and we can then draw a line of best fit through that point. So what I'm saying is we'll draw a line of best fit now onto the scatter graph. The only point it's going to go through is actually a sort of a calculated point, which is the mean of the x's against the mean of the y's. So I'm going to plot on the point 1.6 and against 9.73 as best I can, and then I'll put my line of best fit through that point. So go across to 1.6. Now, as near as we're going to get it, the mean of the y's is 9.7. So go up to 9.7. It's about there. Okay, and plot that point on to the scatter graph, and then draw a line of best fit, and the only point it needs to go through is that point. The actual data points, that as long as it sort of evenly goes through all of them. So the best rule of thumb there is probably think about roughly the same number of points on either side of the line of best fit. So let's see what it would look like. So I could update my graph like that. I've got a title on it now. Scatter graph showing the correlation between engine size and distance travelled on 1 litre of petrol. I'm able to say it's a negative strong correlation. It's negative because the line slopes down, or at least the line slopes down will indicate that it is negative. It means that as one quantity increases, the other decreases. So as you get a bigger and bigger engine size, the distance that you can travel on 1 litre of petrol is less, or it decreases. And that's what I was saying, that the fancier the car, the more expensive it is to run, the less far it will go on 1 litre of petrol. So a negative correlation means as one quantity increases, the other decreases. If it was a positive correlation, the line would slope up, and as one quantity increases, the other quantity also increases. Now, the strength of the correlation, we can judge it by eye. Roughly, if the points are all close to the line, then we would say we have a strong correlation. But we can be more precise about this now, and I'll show you how to do the calculation to give you a measure of the strength of the correlation, and it's called the correlation coefficient. So calculating the correlation coefficient is why we need all these numbers. The x squared column, the y squared column, and the xy column. Now, I've worked them out, and then I've summed the columns, and therefore I can summarize. These are actually the 5 values that I'll need. Sum of the x's, sum of the y's, sum of the x squared, sum of the y squared, and the sum of the xy's. Now, the formulas look a bit scary, and you can do this using your calculator on stats mode, but you may need to use the formulas in the exam. So I'm going to go through how to calculate this using the formulas. And remember, what we're calculating is called a correlation coefficient. It's sometimes called a product moment correlation coefficient, and it is a measure of how strong the correlation is. Okay, so these are the formulas that we need to work out our correlation coefficient, which is sometimes, and very often, it's denoted as R. Now, they look kind of scary, but they're not really. SXX there is really, it's like the standard deviation of the x's, except don't take the square root. And the same with the y's. It's the standard deviation of the y's without square rooting it. And I think I did say that if you don't square root it, it's called the variance. So the variance is the square of the standard deviation. Now, that means these are sort of sensible quantities in their own right. And to work out SXX, which is, as I've just said, the variance of the x's, it is sigma x squared value, which is 20.3, divided by n, which is just the number of pairs of items of data. So we're doing 7 pairs, and then take away the square of the mean of the x's, which is 1.6 squared. So that's all you do. If the formulas may look complicated, but we've used them before really anyway in standard deviation, and if you're careful, you'll be fine. Okay, so we've had a slight issue here in that to do with rounding. There's the values. If I was using that rounded mean of the y's, it's 9.73 rounded. The problem here is that I lose accuracy when I'm rounding, and then my correlation coefficient ends up not being sensible. I'll explain this just in a second. To be more accurate, instead of using 9.73, the formula for the mean without losing accuracy would be, for the mean of the y's, would be 68.1 over 7. So instead of working that out and rounding it, just write it in like that. Now it still needs to be squared. So we're squaring that. I'll get rid of that there and put it there. So we're not losing too much accuracy. Often it wouldn't matter, but our correlation here is so strong that it makes the result not make sense. So we don't need to worry about rounding or about rounding with the mean of the x's, because that's exact. But the rounding was with the mean of the y. So I'm just going to write in the formula for the mean, which is 68.1 over 7, and then use that, so I'm not losing too much accuracy. You always lose some accuracy when you round values. So, and again, really, I should be doing the same thing there. Instead of using the 9.73, the rounded value for the mean of the y is 68.1 over 7. And then my values will come out about that. And then I use this formula here, which is the final formula in all of this. For the correlation coefficient, it's the SXY value, which works out to be minus 1.42 approximately, divided by the product of the square roots then of SXX and SYY. So slot all that in, and the answer is minus 0.99. Now that is telling us we have a very strong correlation, because the correlation coefficient should be giving a value between minus 1 and plus 1. The problem there when I was rounding was I was getting something outside of that range very slightly, and it was because I was introducing an error by rounding. But I've fixed that, and it's a more sensible answer now, and it's an answer that we would expect for this set of data, because it's indicating it's very close to minus 1, which is indicating a strong negative correlation. As we move across the scale between minus 1 and plus 1, we go along into weak negatives. You can take a cut off there as about minus 0.6, and anything up from minus 0.6 to 0 call a weak negative correlation. 0 is no correlation, and then we go into weak positive correlation, and if we got something that was very close to plus 1, we would say we have a strong positive correlation. But if you remember our data and our line of best fit, it showed us anyway roughly that we were expecting to get a negative strong correlation. And so when you think of that in terms of the correlation coefficient, that means you're expecting a value that's close to minus 1. So there's a calculation of the product moment correlation coefficient. And in this example, as I say, we should end up with it very close to minus 1, and we do.